Alright, so I'm going to jump into section 6.6. It starts off with some problems that it'd be nice if you could do without your calculator, but if you need your calculator, it's completely fine. It kind of depends on how well you do numbers in your head, whether you can do these without your calculator or not. So I'll do each problem by hand just to show you what I'm thinking, but you certainly can resort to your calculator if you can't do these in your head. So problem 2 is asking the question, 3 to what power is 9 squared? Because a logarithm always asks the base to what power is the argument. The base is 3, the argument is 9 squared. And then you need to know your exponents really well to be able to do this without a calculator. 9 squared is 81, and I know my powers of 3 well enough to know that 3 to the 4th power is 81, so that if I do this on my calculator, it's going to tell me the answer is 4. It's not really x equal to 4 because the original problem doesn't have an x. I just kind of inserted an x to make the problem up that needed to be solved without a calculator. So my calculator smokes on these logarithms, so I'll just do the logarithm base 3 of 9 squared, and as quick as I could enter it, it gives me the answer of 4. Problem 4 asks the question, the base 7 to what power is equal to 1? And again, I know my exponents well enough to know that the answer is going to be 0, because anything to the 0 power is 1. Again, this is effortless to enter on my calculator. So if I did the log base 7 of 1, I'd get 0. This is probably time to mention a rule if I hadn't already. The logarithm any base of 1 is 0. So that would mean the log base 2 of 1 is going to be 0. I'll just do these on my calculator real quickly. There's the log base 2 of 1. It's 0. If I did the log base 3 of 1, it equals to 0. If I did the log base 4 of 1, it's also equal to 0. This is because each one of these questions is asking us a number to what power is equal to 0. The first one up here is asking 2 to what power is 0. The second one's asking 3 to what power is 0. Is 1, should I say. It's asking 2 to what power is 1, 3 to what power is 1, 4 to what power is 1. And because anything to the 0 power is 1, that's why the logarithm of 1 any base is 0. And abstractly, you might see in a text this written as a rule. The log base b of 1 equals to 0. This means that no matter what the base is, if the argument is 1, the logarithm is equal to 0. As we get deeper into this section, we're going to get a bunch of rules for logarithms, and the main bulk of this section is just learning how to understand the rules for logarithms and how to use the rules. More complex rules than this. Six would be, hard to do without my calculator because the numbers are big. But the question that's being asked is 6 to what power is 2 to 16. I know the answer is 3 because I know my powers of 6 in my head. So if you didn't know that 6 to the 3rd power is 216, your calculator does. So if I do the log base 6 of 216, it comes back with the 3. If I was doing by hand number 8, I'd have to think of the problem in its non-shorthand form. ln is a desirable form for writing because it's less to write, but because ln is the same as log base e, if I was trying to figure out what this is by hand, I'd think of this version of the problem because ln and log base e are interchangeable. So the question that this is asking is e to what power is e to the 4th, or e to the x power is e to the 4th. Sometimes I use question marks, sometimes I use x's, doesn't kind of matter. The answer is 4 because e to the 4th power is e to the 4th power. On my calculator, this is going to be super easy to enter because I could use, my calculator has that ln key. So to figure out the answers for in my calculator, I do ln and then shift in ln to get the e, give it the exponent 4, get out of the exponent, close out my parentheses. That looks just like that, and I get 4 for the answer. If you're clever, doesn't matter that the base is e, any base, if the 1's the argument, the answer is 0. That rule that I just described even applies when the base is e. ln is base e. This is really the log base e of 1. And when I do this on my calculator, so I wouldn't even do any thought. I immediately, when the argument is 1, regardless of what the base is, the answer is going to reduce to 0. If I do this now, ln of 1 on my calculator, it's smart enough to know that as well. 12 is monstrous without a calculator. I think 25 squared is, yes. So the question that needs to be answered without a calculator is 5 to what power is 25 squared? That is 5 to what power is 625? I think that's 4 again. A lot of 4s on these problems. I think 5 to the 4th power is 625. But I would assume almost nobody would do this strategy when you have a calculator that does logarithms so easily. So on my calculator, log base 5 of 25 squared, it is 4. So I think that's the end of the first style of problems. The second style of problems, I'm going to lecture for a good 15 minutes before I, I'll lecture for a few minutes before I do 14, then a few more minutes before I do 16, and then a few minutes after that. Each one of these problems, 14, 16, and 18, illustrate a rule of logarithms. So basically, we're going to learn 3 rules of logarithms in this section, and they're bidirectional rules, meaning they work in 2 directions. So the first rule of logarithms that we're going to need to know for this section is, I call it the sum to product rule. And then you might also call it the add to multiply rule, because adding and sum are kind of interchangeable words. Product and multiply are interchangeable words. I don't know that there's really a specific name for this, but this is just what I happen to call it. And the rule says, symbolically it says this. It says the log base b of x plus the log base b of y, here's the sum part, equals the log base b of x times y. I'm going to put the x times y in a parentheses with a time sign between them. I'll probably get lazy and not be so consistent with the time signs. Let me show you what this rule means in terms of things you can check on your calculator. So this rule tells me this. Let's first, that this should be a true statement, that the log base 2 of 8 plus the log base 2 of 16 should equal to, so in this problem, the b is 2, the x is 8, the y is 16. That should equal to the log base 2 of 8 times 16. And let me show you that it's true, and maybe you can do it yourself. I'm going to show you that this is a true statement by doing each side on my calculator. I'm going to show you that the rule actually works. So I'm going to do the log base 2 of 8 plus the log base 2 of 16. So that's simplifying the left side of this equation on my calculator. And this reduces to 7. Now let me do the right side. The right side says the log base 2 of 8 times 16, which is also 7. So this is an example of how the statement works. It turns out that this statement, or this rule, can apply to more complicated problems, like the log base 5 of 25 squared plus the log base 5 of 125. This rule says that I'm adding two logarithms that are the same base, that I can accomplish or simplify this by rewriting it as the log base 5 of 25 squared times 125. And then let me show you again that this is a true statement. So I'm going to do the left side, which is the log base 5 of 25 squared plus the log base 5 of 125. And the left side simplify to 7 again. These all aren't going to equal 7. And then the right side, if I do it for this rule to be applied right, must also equal 7. So the right side is log base 5 of 25 squared times 125. And that also equals 7. This rule applies even if you're adding more than two things. Like if I had like this, the log base 3 of 81 plus the log base 3 of 27 plus the log base 3 of 9. Even though the rule only has two logarithms being added, it extends to more than two logarithms. This is actually going to equal to the log base 3 of 81 times 27 times 9. And let me show you these again on my calculator. So left side is log base 3 of 81 plus the log base 3 of 27 plus the log base 3 of 9. This left side comes out to be 9. If I do the right side on my calculator, I do the log base 3 of 81 times 27 times 9, and it also equals 9. So I can help you understand how the rule works, kind of going from the sum to product. When we get into the text or into the handout itself, the kinds of problems that are going to be using this rule in this direction would be like this. Write, the instructions will say this, write as a single logarithm. And unfortunately, when we get into the text, the problems won't have numbers that I can check on my calculator. So this might be a problem once we get into the packet problem that is going to be that we'll need this rule for. So the instructions that are going to tell me to use the sum to product rule will be write as a single logarithm. And here I have three logarithms, same base being added together. I can't tell you what this equals to because I don't know what x, y, and z are in terms of a number, but I can tell you what it can simplify to. I can simplify multiple logs being added together with the same base using the sum to product rule. So the sum to product rule says this reduces to the log base 2 of x times y squared times z to the fourth. I probably don't really need to write the times signs between the x, the y, and the z because the times is implied. And if I gave you something even like this, the log base b of w to the 6th power plus the log base b of the square root of x, I can still write this as a single logarithm because it doesn't matter how complicated the argument of the logarithm is. If I have two logarithms being added and their bases are the same, I can use the sum to product rule to rewrite those two logarithms as one logarithm. So that's one direction we're going to use the rule. Like I said, It's a bidirectional rule, which means I could do it forwards and backwards. And in the text, when our author wants us to go or when I want you to go the other way, because I wrote all these problems, the instructions might be, instead of write as a single logarithm, when we get in the packet, we're going to see the instructions that will say write as a sum of logs. And very specifically, if I see the word sum, that means I need to see a plus sign. If I see logs plural, I'll see more than one log. And let me do a problem I could check on my calculator. So let's do the log base 2 of 16 times 64 times 8. So if this was a problem in the text and the instructions said write as a sum of logs, that implies I want to expand this to more than one logarithm. That I have one logarithm and I want to write something that's equal to the logarithm that is a sum of logarithms. So going backwards, this would be the log base 2 of 16 plus the log base 2 of 64 plus the log base 2 of 8. That's just going backwards. If I have multiplication inside a single logarithm, I could expand from a single log to a sum of logs. And let me show you that these equal to each other. The original was log base 2 of 16 times 64 times 8, which was 13. And my expansion into a sum of logs is the log base 2 of 16 plus the log base 2 of 64 plus the log base 2 of 8. And that also equals 13. So I was able to actually check that my expansion is right. The handouts in the text that are the packet that have the instructions right as a sum of logs might look something more like this. The log base b of x to the 4th y z squared. And they asked me to write it as a sum of logs. So I couldn't check this on my calculator, but I still can use the rule backwards. If I have, within a logarithm, if I have multiplication, I can expand from one log to as many logarithms as there are items being multiplied if I use the sum to product rule in reverse. And this is going to equal to the log base b of x to the 4th plus the log base b of y plus the log base b of z squared. So that's the first of 3 rules that we need to be aware of. And in the packet, problem 14 just emphasizes how to use this rule properly. So I don't like the time sign that's written there. Problem 14a says, is this a true statement? Is the log base 3 of 3 times 27 equal to the log base 3 of 3 plus the log base 3 of 27? I think this is true. I think this is true because this is exactly the rule. It says if there's multiplication inside a logarithm, I can take a single log and expand it into a sum of logs. And I'm going to check. This is super easy for me to check. So is the original problem the log base 3 of 3 times 27, which is 4, does that equal to the log base 3 of 3 plus the log base 3 of 27? And it does. So it works this way. A lot of students will blow this rule a little bit and do this rewrite, saying the log base 3 of 3 times 27 equals to the log base 3 of 3, and then instead of putting a plus sign between them, put a time sign between them. I know that this side is still the original 4. If I put a time sign as opposed to a plus between, it doesn't work. The rule doesn't work. So to show you this, if I did this, the log base 3 of 3 times the log base 3 of 27, I get 3. So this is not a true statement. This one's false. So this is just hammering down that this sum to product rule says if I have a multiplication inside a logarithm, I could expand a single log to a sum of logs. I can't expand a single log to a product of logarithms. So the part B is not using the rule correctly, because the rule says multiplication inside one logarithm can be expanded to multiple logarithms if I put a plus between the logarithms and not a times. 16 uses a different rule, and that's the rule I need to talk about next. So I'll come back and do 16 in a bit, but first I need to introduce the next rule. And I'm going to call the next rule the difference to quotient rule. And then if you don't like the big math words, difference is the same as minus or subtract. Quotient means divide. And it's a bidirectional rule again. And I usually present the rule like this. The rule says the log base b of x minus as opposed to plus the log base b of y equals the log base b of x divided by y. Put it in a parentheses. A lot of times I don't use the parentheses, but it's kind of nice to use them. So there's the minus. The minus is between the logarithms. There's the divide. I'll give you a numerical example of how the rule works. My calculator forces these parentheses on me, and it's kind of nice to put them in. But a lot of times, if the logarithm just has a single letter for its argument, I don't throw the parentheses in. But let me be consistent with my calculator. So if I did this rule, the log base 2 of 64 minus the log base 2 of 2. So I'm subtracting two logarithms the same base. The minus to divide rule, or the difference to quotient rule, says that this, the log base 2 of 64 over 2, should be one logarithm that equals to the other one. So let me do the left side. Log base 2 of 64 minus log base 2 of 2. The left side equals to 5. You can even see that. And I'll show you that the right side also works. On the right side, if I do the log base 2 of fraction 64 over 2, I get 5 as well. This rule is a little bit harder to expand to 3 terms, and but it does work, and it's tricky to work it. So I should talk about it. So let's try this. The log base 2 of 128 minus the log base 2 of 4 minus the log base 2 of 16. There's an ugly way to write this, and a not so ugly way. Now I'm going to focus on the not so ugly way. Let me figure out what this equals to. So this is equal to the log base 2 of 128 minus the log base 2 of 4 minus the log base 2 of 16. So these 3 logarithms condense to 1. That's not right. Really. 4 times 6 should be 2. I messed up somewhere, so let me re-enter this. I was so worried about you being able to see what I was typing that I must have typed something wrong. Log base 2 of 128 minus the log base 2 of 4 minus the log base 2 of 16 equals to 1. Huh? Oh, it does equal to 1. Okay, I understand now. I was doing math in my head and I was making a mistake. There's the danger of doing math in your head. So this whole thing equals to 1. I want to create one logarithm with base 2 and the numbers 128, 4, and 16 that also reduces to 1. So I want to find out something, the log base 2 of something, a single logarithm, and I want it also to equal to 1. So I have to decide where to put the 128, the 4, and the 16 to properly use the minus to divide rule slickly, I guess. So you can play around on your calculator and try to get a fraction in there with the numbers 128, 4, and 16 placed properly in the numerator and the denominator, and you might be able to discover the right way to do it. It turns out that the difference to quotient rule, when you try to expand the number of logarithms, you have to be careful of where you put the letters or numbers in this case. It turns out the only way this is going to work is if any logarithm that has a minus in front of it, its argument has to wind up in the denominator. I claim that this one is also going to equal to the same one. So let me show you that, if I can actually make this appear okay. So I'm going to do this logarithm, logarithm base 2 of fraction 128 over 4 times 16. More or less that's that with a different looking times, and that's also going to equal to 1. If I put the 4 or the 16 in the numerator, I wouldn't get the same result. Let me do a different problem that's going to use the difference to quotient rule with 3 logarithms again. I'm going to basically take this same problem, log base 2 of 128 minus the log base 2 of 4, and then plus the log base 2 of 16. I'm going to figure out what this equals to. So log base 2 of 128 minus log base 2 of 4 plus log base 2 of 16. And this one equals to 9. Now I want to create one logarithm, base 2, with the numbers 128, 4, and 16 that equals to 9. And generally, I shortcut all of these difference minus to divide rules. And when I'm using the minus to divide, if a logarithm has a minus in front of it, the arguments wind up in the denominator. So in the last problem, both 4 and 16 had minuses in front of them. When I wrote them as a single logarithm, I put the 4 and the 16 in the denominator. In this problem, only the 4 has a minus in front of it. When I use the rules to write this as a single logarithm, I'm going to use them a little bit differently, and I'm actually sneaking in the first rule. And I'll talk about that in a second, but I claim that this is going to work. 128 times 16 over 4. That's also going to give me 9. So when I'm condensing from multiple logs into one logarithm, if I have to use the minus to divide rule, if a logarithm has a minus in front of it, its argument winds up in the denominator. If an argument has a logarithm has a plus in front of it, its argument winds up in the numerator. Let me show you this also equals to 9, and then talk about how I snuck in the first rule without really mentioning it. So when I do that logarithm, that's what I wrote there. I want it to equal 9, and it does equal to 9. If you do anything else with the numbers, if you put the 16 into the denominator, you get 1. If you did something different with the 128, you're not going to get 9. This is the only way to correctly rewrite this. Had I presented the problem like this, the log base 2 of 128 plus the log base 2 of 16 minus the log base 2 of 4, you'd have seen I'm starting to use 2 rules. These 2 logarithms could be condensed into one logarithm using the sum to product rule. I could have, in steps then, made this the log base 2 of 128 times 16 minus the logarithm base 2 of 4, and then used the minus to divide rule to make this the log base 2 of 128 times 16 over 4. I'm going to write a few more problems down with numbers so we can check, and my whole goal is to write as a single logarithm. So for each one of these problems, my goal is going to be to write as a single log. So let me make some easy problems and hard problems and try to blend these rules together. So first one, log base 3 of 81 minus the log base 3 of 9 plus the log base 3 of 27 minus the log base 3 of 3. I'm going to figure out what this actually equals to as a number because I can. So log base 3 of 81 minus log base 3 of 9 plus log base 3 of 27 log base 3 of 27 minus log base 3 of 3. So assuming I've entered this right, this whole thing is equal to 4. I want to be able to, instead of doing 4 logarithms, find one logarithm, base 3 with the numbers 81, 9, 27, and 3 that also equals to 4. And I'm going to shortcut and kind of blend the rules together. And how do I do that? So if I'm asked to write something as a single logarithm, first of all the logarithms have to be the same base. I know the rules, the minus to divide, the plus to times. If I want to use the rules how we really use the rules, I look at the logarithms that I'm trying to condense. The bases are the same. Any logarithm that has a minus in front of it, its argument winds up in the denominator. Any logarithm without a sign, which is an implied plus, or that has a plus sign, winds up in the numerator. So I claim that that's a proper way to rewrite this as a single logarithm. That both the 81 and the 27 are going to belong in the numerator because they're kind of using the sum to product rule and they were being multiplied. The 9 and the 3 belong in the denominator because I'm using the minus to divide rule. And let me make sure that that actually works. So let me do logarithm base 3 fraction 81 times 27 over 9 times 3 equals. And it magically, well, you can't even see it, but it also equals to 4. Let me do one more with numbers. The log base 2 of 4 minus the log base 2 of 64 minus the log base 2 of 16. So this isn't really radically different than something that we've seen earlier. Let me figure out what it equals to first. So what it equals to, I do log base 2 of 4 minus log base 2 of 64 minus log base 2 of 16. This whole thing equals to -8. I want to come up with one logarithm, base 2, that's equal to -8. So how do I do that? I write one logarithm base 2. I see minuses, so I know I need a fraction. And both the 64 and the 16 will wind up in the denominator of the fraction because they both have negatives in front of their logarithms. The 4 is going to wind up in the numerator. So I claim that that's also going to equal -8. And this is successfully writing these 3 logarithms as a single logarithm. So let me check. The log base 2 of 4 over 64, delete, 4 over 64 times 16. And that also equals -8. So I know that I've successfully rewrote this. Let me do a couple problems with letters because once we get into the packet problems, they're going to have letters and not numbers. Same instructions, write as a single logarithm. How about this? The log base 2 of x squared minus the log base 4 of y to the 4th. Base 2, the bases have to be the same or you can't use the rules, plus the log base 2 of z. So I have 3 logarithms, all base 2. If the bases weren't the same, you can't make one logarithm from multiple logarithms unless the bases are the same. So I'm going to shortcut this, use both kind of the minus to divide rule and the adding to multiply rule. This, I couldn't check on my calculator, but I know this is correct because I know how to shortcut these rules or how to use the rules in conjunction. So immediately I know my single logarithm is going to be base 2. I know that I'm going to have an x squared and a z in the numerator because the x squared didn't have a sign in front of it, so that's an implied plus. The z had a plus in front of it, but the y had a minus in front of it. I'll do one more of these, and I'll do some backwards ones. So how about the log base b of w to the 4th plus the log base b of y minus the log base b of x squared. If I wanted to write this as a single logarithm, it starts off as 3 logarithms. They're all the same base, so they can be condensed into one logarithm. And when I condense them, the base doesn't change. If I see a minus, I know I need a fraction. If I don't see a minus, then I'm not going to need to use the minus to divide rule. I'm just going to use the adding to multiply rule. And in the numerator of this is going to be both a w to the 4th and a y because those both have pluses in front of them. And the denominator is going to be an x squared. The alternate way that we'll have to use the rule, the instructions might say this: expand into a sum and or difference of logarithms. So I'm going to start with one logarithm. I'll do it with numbers first. The log base 2 of 4 times 16 over 256. This is one logarithm, and I want to expand this into as many numbers that are being multiplied, so I want to expand it into 3 logarithms. Let me figure out what this equals to real quickly. This equals to the log base 2 of fraction 4 times 16 over 256. So this is equal to negative 2. I'm going to expand this into 3 logarithms, one with a 4 as the argument, one with a 16, the other as a 256. And I want to put signs between the logarithms such that when I do them separately, I get the same negative 2. So I want to come up with a log base 2 of 4, a log base 2 of 16, and a log base 2 of 256. And I want to throw the appropriate plus and minus signs where they go, so that this whole 3 logarithms, I'm expanding from one logarithm into a sum and or difference of logarithms, that I'm going to get negative 2 again. And immediately when I'm expanding, if something is in the denominator of a fraction, its logarithm has to have a minus in front of it. If it's not in the denominator, then it's either first without a sign or it gets a plus sign. So I think that's going to work. And let me make sure that that works. I'm going to do the log base 2 of 4 plus the log base 2 of 16 minus the log base 2 of 256, at best equal to negative 2. And it does, so I know I've used the expansion rule, my rules properly. Let me do one more. Log base 3 of 9 times 27 over 81 times 3. So I want to expand this into 4 logarithms. Let me figure out what it equals first. So log base 3 of fraction 9 times 27 over 81 times 3. This whole thing equals 0. Wow. All right. So that means I need to come up with 4 logarithms, all base 3, one with a 9, one with a 27, one with an 81, and one with a 3. I need to get signs between the logarithms. Either plus or minus are the only signs I'm allowed to use here, otherwise I'm really not gonna have a chance at the right answer. And both The 9 and the 27 don't deserve minus signs because they're not in a denominator. The 81 and the 3 do get minus signs. I claim if I do log base 3 of 9 plus the log base 3 of 27 minus the log base 3 of 81 minus the log base 3 of 3, I'm going to get that 0. So let me try that. So log base 3 of 9 plus log base 3 of 27 minus log base 3 of 81 minus log base 3 of 3. If I've successfully rewritten it, I'm going to get a 0. And I do. So I've used the rules perfectly to expand this into both a sum and difference of logs. I'll do a problem with some letters just so you can get a vibe for how it's going to be when we get to the packet. So in the packet, I might see something like this: the log base b of x squared y over z. And I'll be asked to expand into a sum or difference of logs. That's going to imply that I want one logarithm for each letter. So I'm going to have 3 logarithms. All are going to be base b. One's going to have an x squared. The other's going to have a y. And the third is going to have a z. I just have to decide on the signs. I can't check this on my calculator because I don't know what x, y, nor z are. But I know that when I'm expanding from one log into multiple logs, if there's a fraction, that's the only time I need a minus sign. If there's no fractions, it's all adding. I'm just using the product to sum the product rule. And in this problem, only the z is going to pick up a minus because it's the only letter in the denominator. Almost ready for the packet. I'm going to do this problem in the packet just to illustrate how the rules do and don't work. Hopefully. So problem 16 gives me a part A and a part B. One part is true, one part is false. And I'm supposed to decide which one of these is true, which one is using the rules properly. When I look at part A, I can do both on my calculator. Part A gives me the log base 3 of the fraction 81 over 3. And the left side equals to 3. Let me do the right side. The right side is fraction log base 3 of 81 over the log base 3 of 3. And that equals to 4. So this one's clearly false because this one isn't using the rule correctly. The rule that's being focused on here is if you have a divide inside a logarithm, when you separate from one logarithm to 2 logarithms, you don't divide the logarithms, you have to subtract the logarithms. This bottom one's going to be the true one. So this is the false one. This is not using the divide to minus rule properly. Whereas the bottom one, I have a logarithm of 81 divided by 3. I'm separating it into a logarithm of 81 minus the logarithm of 3. So I'm going to check that this side gives me that 3 again. So just in case. So I do the logarithm base 3 of 81 minus the logarithm base 3 of 3. And it gives me this one's the true statement. So the problems 14 and 16 and actually 18 are just to kind of illustrate how sometimes students use the rules wrong. Sometimes they go the times to times rule and the divide to divide rule. That's not right. It's multiply to add. It's divide to subtract. And this is just to illustrate that when you're expanding from one logarithm into multiple logarithms, you're never going to multiply logarithms nor divide logarithms. When you're expanding from one logarithm into multiple logarithms, if there's multiplication, you're adding. If there's division, you're subtracting. But you're most certainly not dividing or multiplying when you're going from one logarithm to 2 logarithms. The last rule doesn't make one logarithm into multiple logarithms. It allows you to move exponents around. And I can say maybe the exponent to multiply rule is the last rule that we need to learn. And it's not a rule that allows me to expand logarithms, but it allows me to move exponents around. So here's an example here's what the rule says. The rule says this: if I had the log base b of x to some p power, that equals p times the log base b of x, which tells me if I have an exponent inside a logarithm, I can make that exponent a coefficient and it works the same way. Here's an example of that rule. If I had the log base 5 of 25 squared, which was a problem I did earlier today, the rule says that this is going to equal 2 times the log base 5 of 25. So I'll show you each on my calculator. Left one, log base 5 of 25 squared equals to 4. Rewrite 2 times the log base 5 of 25 also equals to 4. If I did something like the log base 7 of 49 to the 5th power, that should equal 5 times the log base 7 of 49. So the log base 7 of 49 to the 5th power is equal to 10. And on the other side, 5 times the log base 7 of 49 also equals to 10. So that's how the rule is used. If you have an exponent inside a logarithm, you can move that exponent out front and make it a multiplication. That's handy when I'm doing logarithms in my head, because it's easier for me to find the logarithm base 5 of 25, which I knew to be 2, rather than change that to the 625 that I did. Let me go to the little handout questions about this rule and then tell you how we integrate the 3 rules together, because this rule is just kind of integrated with the other rules. It needs, and it's going to be needed at some point. So which of these are the appropriate ways to use the rule? Oh God. So that's going to be 2 to the 4th. That's 4. Okay, so which of these? This one is just using the rule perfectly. Notice I didn't even put a base here, so the base is 10. If I did this on my calculator, I use the log button without the base because it's base 10. The logarithm of 100 to the 4th power. I'm using parentheses because my calculator forces them on me. That equals to 8. And this is exactly that. This just made the exponent and brought it out front and made it 4 times the logarithm of 100. So this is using the rule perfectly. This one's the true statement. That's exactly what the rule says I can do. This next one, I don't think any student would ever do. This is kind of a bad problem. But this still equals to 8. I can't do this. I don't know why you would even think to do this, but this one I think is definitely the false one. So if I try to do this on my calculator, this thing is equal to 16. I can't like bring the exponent outside of the logarithm. That's a horrible problem. I probably should just delete it, but it's there. But this one's using the rule properly. If I have an exponent inside a logarithm, I could bring it out front and make it a coefficient. So in practice, how do we use these? So we have 2 kinds of problems that we're going to get here in a second. One kind of problem is write as a single log. I've done a few of these, but we haven't done any that use this rule. So let me try this. 5 times the log base 2 of 16 plus 4 times the log base 2 of 8. Let me figure out what this equals to. So 5 times the log base 2 of 16 plus 4 times the log base 2 of 8. So this whole thing equals to 32. To write something as a single logarithm, to use the rules, the plus to multiply rule and the minus to divide rule, you can't have coefficients. The rules, when I wrote the rules down, they didn't have numbers in front of the logarithms, and they don't work with numbers in front of the logarithms. So if there's numbers in front of the logarithms, before you write 2 logs as a single log, this is where you have to use the multiply to exponent rule in reverse. So to figure out what these logarithms can be, how these logarithms can be written as a single logarithm, I have to use the rule that I just talked about in reverse. Logarithms, if they have exponents, you can bring the exponents out front and make them coefficients. If they have coefficients, you can bring the exponents in and make coefficients and make them an exponent. So this is my original problem that was 2 logarithms. I'm trying to deal with 1 logarithm, something that's equal to that, and this is going to be the one that should work. The log base 2 of 16 to the 5th times 8 to the 4th. So we'll be using the exponent to multiply rule, or the multiply to exponent rule, when we're condensing logs and when we're expanding logs. So let me show you this one actually works. So if I do the log base 2 of 16 to the 5th times 8 to the 4th, for me to be successful here, this has to be 32. And it is. So I've successfully wrote this as a single log. Let me do a more complex problem. 3 times the log base 4 of 64 minus 2 times the log base 4 of 16 minus 5 times the log base 4 of 2. Let me figure out what this equals to and then write them as a single log. So 3 times the log base 4 of 64 minus 2 times the log base 4 of 16 minus 5 times the log base 4 of 2. So these 3 logarithms together go to 5 halves, which is 2 1/2. It's because this logarithm there is not so nice. So this is 5 halves, which is 2 1/2. It's okay to get negative answers. It's okay to get decimal answers. How do I make one logarithm that's going to equal to 5 halves, or 2 1/2? Well, first I make the exponents out of the coefficients. I can't use the minus to divide rule or the add to multiply rule when the logarithms have numbers in front of them. I have to use the exponent rule that I just learned. So I can make this first logarithm the log base 4 of 64 cubed, this one the log base 4 of 16 squared, this one the log base 4 of 2 to the 5th. Now I can make the 3 logarithms into one. They're all base 4, which is nice. In the numerator, I'm going to have a 64 cubed. In the denominator, I'm going to have a 16 squared times 2 to the 5th. Because anything that has a minus in front of it winds up in the denominator with its exponent. So let me see if this equals to 5 halves. It's got to, otherwise I've messed up. So log base 4 fraction in the numerator, 64 to the 3rd power. In the denominator, 16 to the 2nd power times 2 to the 5th power. I'm hoping I see 2.5 or 5 halves, and I do, so I know I've rewrote this correctly. I think this is probably enough that we can jump into and do the problems in the section. And let me do them backwards. And I'll do the 19 through 30 second, and the 31 through 42 first. So 31 through 42 is kind of what I've just been doing. I'm given problems that have more than one logarithm. I'm asked to write them as a single logarithm. In order to take 3 logarithms or 2 logarithms and write them as one logarithm, the logarithms can't have numbers in front of them. So for 32, I need to make this the natural log, which is the log base e of x to the 5th, plus the natural log of y. Notice I don't have the parentheses here because a lot of times when a logarithm just has a single letter, I don't use the parentheses. It's probably better too, but it's understood. The parentheses aren't so necessary when it's just a single x, single y, or single z. So I use the rule that allows me to make exponents into coefficients. Now I can make the 3 logarithms into one. I look at the signs. I don't see any minus signs, so I know I don't need a division. It's all multiplication. My answer to this problem, rewriting the expression as a single logarithm, is going to be a logarithm base e, or natural log, and I'm just going to have an x to the 5th a y, and a z cubed, all multiplying, no fractions because there was no minuses. 34 is nice base 10. I don't see a base, but the base of 10 is implied. If I want to make those two logarithms into one, I know I'm going to wind up having a divide. But before I can make the two logarithms into one, I have to make the coefficients into exponents. Once I do that, once I have the coefficients inside the logarithms as exponents, now I'm going to use the minus to divide rule, and I'm going to get my answer. And again, a lot of times I'm lazy with the parentheses. It's probably nicer to have the parentheses. My calculator definitely puts them in for me. And the difference to divide rule, any logarithm who has a minus in front of it, when you're writing an expression as a single logarithm, any logarithm that has a minus in front of it, its argument winds up in a denominator. Anything with a plus winds up in a numerator. If there's no minuses, there's no fractions. So 34, same sort of issue I have here. I've got three logarithms, all base 10, because 10 is easier for me to type. Each has a number in front of it. And before I make the three logarithms into a single logarithm, I need to use the multiply to exponent rule, or the exponent to multiply rule, because bidirectional, it works both ways. Now I'm ready to make one logarithm out of the three logarithms. The base is 10. I know I'm going to need a fraction because there's a minus, and I know that the only thing that's going to wind up in the denominator is the z cubed, because that's the only logarithm that has a minus in front of it. Both the x and the y arguments wind up in the numerator because they don't have minuses in front of them. 38, same deal. I'm going to make the exponents out of the coefficients to get the logarithm base 5 of x that's squared, believe it or not, minus the logarithm base 5 of y to the 4th plus the logarithm base 5 of z. I'm going to make these three logarithms into one logarithm, base 5. The base doesn't change when you're using these rules. I know I'm going to need a fraction because I see a minus. The y is going to wind up in the denominator, but neither the x nor the z deserve a spot in the denominator because they don't have minuses in front of their logarithms. I have some flexibility of how I handle 40. I would think of it like this: ln of y plus ln of z minus ln of x. If I didn't have that x first, it would be easier to know what to do with it. On problem 40, there's no exponents that I need to make into coefficients, so I don't have to do that first step. What I need to do is condense the three logarithms into one, and I know I need a fraction because I see a minus, and the x is going to wind up in the denominator because it's the logarithm with the minus. The y and the z, their logarithms don't have minuses in front of them. They actually had pluses in front of them in the original problem, so they wind up in the numerator. 42 is, I wouldn't put something like 42 on the test because it has three of the same letters. It's actually going to reduce quite a bit. Let me do it out, but again, it's not that important in terms of it's not going to be on the test. In 42, again, before I can make three logarithms into one logarithm, I need to make the coefficients into exponents. Now I'm going to make one logarithm. The x squared is going to go in the denominator because it has a minus. The x to the 4th and x to the 5th are going to go in the numerator because they don't have minuses. And in all the other problems, my letters were different letters, so the fraction couldn't reduce. But this fraction, because they're all x's, they should reduce. And this is just calling back some rules from chapter 4. In the numerator, if I wanted to combine the two x's into one, I'd add the exponents using the rule that multiplying with letters, you add the exponents, kind of like with logarithms, multiplying goes to add. And I'm going to divide, and the divide goes to subtract, kind of like logarithms again. This would be the best answer for problem 42. Again, I wouldn't put something like 42 on the test. The next problems is going in reverse. I'm going to have one logarithm, and I want to expand it to as many logarithms as I have letters. Whoops. And what did I do with those? Oh, yes. 14 through 30. Okay. 28. 30. Good. Okay, so the second to last group of problems that I want to do is I want to expand the problems between 19 and 30 into more than one logarithm. Generally, it's implied when you're asked to expand that you expand to one logarithm for each letter. And, although it's not written, you usually make exponents into coefficients. So there's multiple answers I would take here. So in problem 20, I know I need to expand into 3 logarithms, one for the x, one for the y cubed, and one for the z to the 5th. When you're asked to expand, generally the problem starts with one logarithm, and you want to make as many logarithms as there are letters. And so I've just done that, and and I need signs between my logarithms because there aren't any fractions. I don't put any minus signs. This is correct, especially based on the instructions. This is definitely, I've expanded this to a sum of logs. A better answer, so this is kind of the okay answer. For whatever reason, when we're expanding logarithms, we usually use the exponent to coefficient rule or exponent to multiply rule and make the arguments a little bit simpler inside the logarithms. This is kind of the better answer for number 20. They're both correct. If you did either of these on a test, I'd be okay with both of them. 22, because there's only 2 letters, when I expand it, I'm going to expand it into 2 logs. 1 logarithm for the x to the 4th, base b, the other logarithm for the y. I have to decide on the sign. The sign that goes in front of the y is minus because it's in the denominator. And again, this, if you did that on a test, that is considered expanded. The instructions are weak, so they don't really tell you to make the exponents into a coefficient. But the better answer, if you go to Math 151, you're going to redo these problems, and the answer that your teacher is probably going to want you to show is that. But they're both correct. They're both they both follow the instructions that I've expanded these into a sum or difference. I can't necessarily do both sums and differences. It kind of depends on the problem. In 24, I'm going to get 3 logarithms because there's 3 letters. They're all going to be base 7. I'm going to have a log base 7 of x, a log base 7 of y, a log base 7 of z cubed. In terms of the signs, because both the y and the z are in the denominators, they get minus signs. That's the okay answer. It would be better to write the log base 7 of x minus the log base 7 of y minus 3 times the log base 7 of z, but I'd accept either. 26, I'm going to expand into 2 logarithms, one with the z cubed, the other with the w squared. I always have to have a sign. It's always going to be a plus or a minus sign between the logarithms. Because there's not a divide, I don't get a minus sign, I must get a plus sign. That's the okay answer. The better answer would be the log base 3 times the log base 3 of z plus 2 times the log base 3 of w. 28 and 30 I wouldn't put on a test, but I just wanted to do them just so you could see some of the evilness that might come up in Math 151. So it's knowing how to make radicals into fraction exponents that your teacher might want you to do. So in 28, I'm going to expand this into 2 logarithms, one for the y, one for the square root of z. They both have to be base 4. Because there isn't a divide, I know the sign next to them would be plus. The big thing in college algebra is this second logarithm. Your teacher might want you to remember that the square root of z is the same as the second root of z to the first, and that can be written as z to the 1/2 power, because square root and 1/2 power are the same. And in a college algebra text for this same problem, you might see this answer as opposed to that answer. I'd live with either answer. I wouldn't even ask square roots on a test. But when you go to Math 151, this whole chapter on logarithms, you basically relive and get it it's almost identical. There's just some word problems that are a little more complicated, but every problem that we've done, you'll probably see again. And this would be a college algebra answer. This is okay for intermediate algebra. Same thing with 30. I'm going to expand this into 1 logarithm for the square root of x, 1 logarithm base 5 for the cube root of y. When I'm expanding, I have to either put plus or minus signs between the logs, not divide or times signs. Because the y is in the denominator, it gets the minus sign. I'd live with that if this was a test question. Again, I wouldn't put these on a test, but this, for me, would be okay answer. If you want to do better, you think of the square root as a 1/2 power, and you make that 1/2 times the log base 5 of x. Notice I'm not using parentheses all the time. It's just, a lot of times we just don't write them, even though it might be better to write them. And then the cube root of y is the cube root of y to the first, which is the same as the log base 5 of y to the 1/3 power. If you're writing without a radical, you make a fraction exponent, and that's the same as the log 1/3 times the log base 5 of y. This is kind of maybe the best answer, as opposed to just an okay answer. But again, I won't ask any problems on the test that have fraction exponents, so they're a non-issue for us. The rest of the problems are just using your calculator, rounding to 2 decimal places. And there's a lot of calculator problems in this chapter because when I wrote the material, the calculators were monsters to work. But now it's so easy, I should just delete these problems. But yeah, go check my rounding skills anyways. So 44, the log base 7 of 14 is 1.356. I look at the number in the 3rd decimal place. It tells me to round that 5 up. I'm going to put a squiggly equals because it's a rounding. I'm going to say this is about 1.36. The next one, the log base 9 of 36. My calculator gives me 1.630. That 0 tells me I don't need to round the 3 up. I'm going to leave it a 3. And say this is 1.63. The next one actually is going to come out to a nice number. It's a negative number. I could do these in my head, but I don't want you to burn your brain cells just yet. But this is actually asking the question, 2 to what power is 0.25, which is 2 to what power is 1/4, and that's actually 2 to the negative 2 power is 1/4. So this one I don't even need to round. I can just make it a flat negative 2. And the last one, the log base 6 of 7, is 1.086. This 6 is going to tell me to round that 8 up to a 9, so I'm going to say this is approximately 1.09. So one section left. It is a long section. It's the section in our class that's most like what you're going to see in college algebra. The big step up in difficulty in college algebra is not that the problems are harder. The problems are probably equivalently difficult. It's just that each section does many more concepts. Most of our sections in intermediate algebra kind of have 1 or 2 concepts. In college algebra, the sections are monstrously long, and they have like 3 or 4 concepts. So that's the section 6, 7 is going to be real typical when you see 151 of what you're going to experience. All right, so that's the end of that section, and let me just shut this down.